Welcome to the Deep Dive. Today we're diving into something that's literally always around us.
Always there.
We're talking atmospheric circulation and weather systems,
Oh, very cool.
all those forces that drive our planet's winds and storms and everything.
Right.
You shared a chapter from a geography textbook with me, and, textbooks sometimes get a bad rap
Mm-hmm.
for being kind of dry.
Yeah.
But I gotta say, this one has some real hidden gems
It really does.
about how the weather we experience every day is created.
Absolutely. And I think, one of the things that I found really interesting
Yeah,
is that just by existing, our bodies are under incredible amount of pressure from the air around us.
it's true. Yeah, it's called atmospheric pressure. And it's like a literal weight
Mm-hmm.
of a whole column of air
Mm-hmm.
from the ground all the way to the edge of space,
Wow.
pressing down on every square inch of everything.
That's a lot to carry around.
Wow. I know it's true.
Yeah, and this pressure is something that we measure in units called millibars. At sea level, the average pressure is about 1,013.2 millibars.
Gotcha.
But as you go higher, like if
Mhm.
you were climbing a mountain, that pressure decreases.
Right. Because, if you think about it like a stack of pancakes,
Okay.
the bottom pancake is always feeling the most weight
Mm.
from all the other pancakes on top of it.
Right.
So the higher you go,
Yeah.
the fewer air molecules are stacked above you,
Makes sense.
meaning less pressure.
Exactly.
So is that why people have trouble breathing
Yes.
at really high altitudes?
Exactly. The air is thinner up there
Okay.
because there's less pressure pushing those air molecules together,
Right.
less oxygen available in each breath.
Oh.
It's like trying to drink a milkshake through a tiny little straw. You just can't get as much.
Oh my gosh, that's a great analogy.
Yeah.
So the chapter also mentions these things called barometers.
Yes.
And there's two main types,
Right.
mercury and aneroid.
Mm-hmm.
So is that how scientists sort of keep track of
Oh, that's great.
pressure?
They're essential tools for meteorologists
What
because
is-
they help us track these pressure changes.
Okay.
And that gives us clues about what kind of weather is heading our way.
Gotcha.
And speaking of weather, pressure differences are really what drive wind.
Oh, okay. Interesting.
It's like when you open a window on a breezy day,
Uh-huh.
the air is going to rush in or out,
Okay.
depending on whether there's higher pressure outside or inside.
So wind is just air moving from a high pressure zone to a low pressure zone.
Yes, you got it.
Trying to even things out.
Exactly. It's always trying to reach a state of equilibrium.
Okay.
But there's a little more to it than that.
Okay,
It's not quite that simple.
Okay.
There are actually three main forces at play that shape how the wind blows.
Okay.
We've got the pressure gradient force, like
Mhm.
that window example you just mentioned.
Right.
But we also have frictional force.
Okay.
And then there's this really fascinating thing called the Coriolis effect.
The Coriolis effect.
Yeah, have you heard of that?
Yeah. It sounds a little bit complicated, though.
It is fascinating, though.
Okay.
So imagine you're trying to roll a ball
Okay.
straight across a spinning merry-go-round.
Mm-hmm.
Instead of going in a straight line, the ball appears to curve
Okay.
because the merry-go-round is moving underneath it.
Gotcha.
Same thing happens with the wind on Earth.
Interesting.
Because our planet is constantly rotating, the wind doesn't just blow in a straight line
Mm-hmm.
from high pressure to low pressure.
Right.
It gets deflected.
Okay.
And that's the Coriolis effect.
So it's like an invisible force
Mm-hmm.
is nudging the wind off course
You got it.
because of Earth spinning.
Precisely.
I bet that creates some pretty interesting patterns.
Oh, it does.
Yeah.
In the northern hemisphere, winds are deflected to the right,
Mm-hmm.
and in the southern hemisphere, they're deflected to the left.
Wow.
That's why hurricanes, for example, spin counterclockwise in the north
Oh, wow.
and clockwise in the south.
Okay.
And the Coriolis effect isn't just a scientific curiosity. It's actually factored into things like
What?
long-range missile trajectories.
Really?
Uh-huh.
Wow. I never realized the Earth's rotation had such a big impact
It's pretty amazing.
on things like wind and even missiles.
Yeah.
So we've got these pressure differences creating wind
Mm-hmm.
and the Coriolis effect making it all swirly.
Yeah.
What happens next? Does that lead to those big global wind patterns I've heard about?
You're on the right track.
Okay.
So imagine the Earth as this giant, unevenly heated ball.
Okay.
This uneven heating creates bands of high and low pressure
Yeah.
that circle the globe.
Okay.
And these are the driving forces behind those global wind patterns.
Okay, cool.
Yeah.
The textbook mentions some names for these pressure belts,
Right.
like the equatorial lows,
Yeah.
subtropical highs, subpolar
Mm.
lows, and polar highs.
Yeah, all different areas of pressure.
Do these different pressure belts explain why some parts of the world, like the tropics, have such consistent climates?
Yes, exactly.
Interesting.
So think about the Sahara Desert, for example. Okay. Its hot, dry climate is a direct result of the consistently high pressure
Uh-huh.
of the subtropical high pressure belt that dominates that region.
Gotcha.
And these pressure belts aren't static.
Okay.
They shift and interact, which influences large-scale wind patterns,
Okay.
like the trade winds that blow towards the equator.
So it's like these pressure belts act like giant air traffic controllers
That's a great way to put it.
for the wind.
Yeah.
That's interesting.
It really helps to visualize, how all these elements, pressure, wind, even the Earth's rotation come together
Uh-huh.
to create this massive dynamic system that's always in motion.
It's like a giant engine
It is.
driving weather patterns around the world.
It is.
But it's not just the atmosphere, though.
Right.
I remember reading that the oceans
Yes.
are also part of this whole global weather system.
Absolutely. You're absolutely right. And
Yeah.
the relationship between the atmosphere and the oceans is fascinating.
Okay.
They're constantly influencing each other. Uh-huh.
In a delicate dance.
Yeah.
We were just talking about how wind is driven by these pressure differences.
Right.
But those winds don't just move air.
Yeah.
They also push the water around,
Uh-huh.
creating ocean currents.
So the wind is like an invisible hand stirring the oceans.
It really is incredible, isn't it?
That's so cool.
Yeah.
And then the oceans, in turn,
Right.
affect the atmosphere.
Exactly.
It's like a loop.
It is a loop.
It's all connected.
That exchange of heat and moisture between the air and the water influences those same wind patterns.
Wow.
Creating this incredibly complex feedback loop.
So I'm starting to see how all these big global forces, like wind patterns and ocean currents, can actually impact,
Yes.
the weather I experience in my own backyard.
Exactly. It all ties together.
Wow.
And that brings us to something called the three-cell model of atmospheric circulation.
Okay, 3-cell model. Sounds a bit technical.
It does sound a little jargony. Yeah.
But I promise it's not that complicated.
Okay.
Imagine taking the atmosphere and dividing it up like a cake,
Right.
with 3 slices in each hemisphere.
Mm.
The Hadley cell, the Ferrel cell, and the polar cell.
Okay.
These cells act like giant conveyor belts moving heat energy
Okay.
from the equator towards the poles.
Gotcha.
It's like a global air conditioning system,
Wow.
trying to distribute the sun's heat more evenly.
Okay, so warm air rises at the equator,
Yes.
travels toward the poles,
Mm-hmm.
then cools down and sinks back down.
Exactly.
Gotcha.
And this circulation, combined with the Earth's rotation and the Coriolis effect we talked about,
Right.
creates the major wind patterns we see,
Okay.
like the trade winds and the westerlies,
Gotcha.
which blow predominantly from west to east in the mid-latitudes.
So we've gone from invisible pressure pushing down on us
We have?
to massive cells of air circulating the whole planet.
It's quite a journey.
And this is all just the beginning of understanding how weather works.
It's a complex system, but fascinating once you start to unravel it.
It really is.
Yeah, and this interconnected system is also responsible for some of the larger scale weather patterns we see,
Okay.
like El Nino and La Nina,
Oh, yeah, those are the big ones.
the big global events.
Yeah, they seem to affect the whole world.
They do.
But I never really understood what causes them.
Right, they're kind of mysterious to a lot of people.
Yeah.
So they're a great example of just how closely linked
Okay.
the atmosphere and oceans really are.
Gotcha.
El Nino and La Nina are essentially fluctuations in the temperature of the surface waters
Okay.
in the central and eastern Pacific Ocean.
Wait, so changes in ocean temperatures can actually shift weather patterns across the entire globe?
They can. It's pretty remarkable.
That's crazy.
Think of it this way. The Pacific Ocean is huge, right?
Yeah.
When its surface temperatures change, it disrupts the normal atmospheric circulation patterns above it.
Gotcha.
That can trigger a chain reaction,
Right.
leading to shifts in rainfall patterns, droughts in some areas, floods in others,
Wow.
even influencing the intensity and paths of hurricanes.
That's wild.
So scientists keep a very close eye on El Nino and La Nina
Yeah.
because of their potential for widespread impacts.
Okay, so we've covered this big picture. We
Mhm.
talked about pressure,
Right.
wind patterns, global circulation,
Yeah,
even how the oceans play a role.
it's all connected.
But what about those more local winds that we experience every day?
Right?
Like the breeze at the beach or those gusts that come whipping through mountain valleys?
Question.
Are those caused by these same forces?
They are. It's all about those pressure differences and that heating and cooling.
Okay.
Just on a smaller, more localized scale.
Okay, cool.
Yeah. So let's explore how those work.
Right.
So think about a day at the beach.
Okay.
That refreshing sea breeze you feel.
Yeah.
That's a perfect example of how land and water heat up at different rates,
Uh-huh.
creating localized winds. During the day, The land heats up much faster than the ocean.
Makes sense.
That warmer land heats the air above it,
Okay.
causing it to rise,
No.
which creates an area of low pressure.
So it's like the land is exhaling warm air,
Yes, good analogy.
creating a bit of a vacuum.
Exactly. And since nature abhors a vacuum,
Right.
the cooler, higher pressure air over the sea
Yeah.
rushes in to fill that space,
Gotcha.
giving you that cool sea breeze.
Okay.
Then at night, the situation reverses.
Wow.
The land cools down quicker than the ocean.
Right.
Now the wind blows from the cooler land out over the warmer water.
That's like the land is breathing in and out.
It is. It's like this constant cycle.
That's cool.
And you've probably noticed that shift on beach trips.
I have, wait,
The wind seems to change direction as the sun sets.
for sure.
It's a subtle shift,
Yeah.
but it's there.
It is definitely.
And the same principle applies to those winds you mentioned in the mountain valleys.
Oh, cool.
During the day, the sun heats up those mountain slopes, causing the air to warm and rise,
Yeah.
creating what we call a valley breeze, as
Mhm.
cooler air flows up from below to replace it.
Right.
Then at night, the slopes cool down.
Yeah.
That denser, cooler air flows down into the valleys,
Got it.
creating a mountain breeze.
So the same idea as the land and sea,
Exactly.
just with mountains.
It's all about that differential heating and cooling.
The mountains are breathing.
They are.
That's cool. I love how these same principles apply at different scales.
It really shows you how interconnected everything is in the atmosphere.
Yeah.
These processes might seem small compared to, those giant global wind patterns,
Right.
but they can have a big impact on local weather and ecosystems.
Okay, so we've got these local winds.
Yep.
And these giant global winds.
Mhm.
And the oceans are stirring things up.
Yeah, it's a party up there.
But what about when the weather takes a more dramatic turn?
Okay.
Like when a cold front rolls in
Yeah.
and suddenly it's time to break out the sweaters.
Right.
Got to bundle up.
What's happening there?
Ah, that brings us to the fascinating world of air masses and fronts.
Ooh.
Imagine these enormous bubbles of air,
Okay.
each with its own distinct personality,
Uh-huh.
a specific temperature and humidity.
Okay.
We call these air masses.
Okay, so an air mass that forms over the ocean would be pretty humid,
Very humid.
and one hanging out over a desert would be bone dry.
Exactly, you got it.
Okay, cool.
And these air masses don't just sit there. They
Right.
travel around the globe,
Okay,
carried by those global wind patterns we talked about earlier.
gotcha.
And when two air masses with different personalities meet,
Uh-oh.
that's where things get interesting.
Okay.
That clash is what gives us our weather changes.
So like when a cold, dry air mass
Yes.
bumps into a warm, humid one?
Exactly. That's a recipe for some dramatic weather.
It sounds like it.
It can be.
Yeah.
The boundary between two air masses is called a front.
Okay, a front. Yeah, and there are different types of fronts, cold, warm, stationary, and occluded each with its own set of characteristics.
Right.
And they bring their own kind of weather.
So when I hear on the news that a cold front's approaching,
Yeah.
what does that actually mean? What's happening?
Picture this. A mass of cold air is like a giant invisible bulldozer
Okay.
pushing its way into a region occupied by warmer air.
Uh-huh.
That denser cold air wedges underneath the warmer air,
Okay.
forcing it to rise rapidly.
So that rising warm air is what creates those towering clouds
Exactly.
and heavy precipitation
Yes.
that often come with a cold front.
You got it. Cold fronts are notorious
Yeah.
for bringing sudden changes like thunderstorms, heavy rain,
Right.
even hail or snow, depending on the season.
Oh, wow.
After the front passes, you're left with colder air and clearer skies.
It's like the air masses are battling it out.
It is a battle.
And we experience the results as changing weather.
That's a great way to put it.
That's really interesting.
Yeah.
And sometimes these battles can escalate into full-blown storms.
Oh, absolutely.
Oh, yeah, storms.
Now, those are some dramatic weather events.
Yeah, they are. The textbook mentioned different types.
Right?
Extratropical cyclones,
Hmm.
tropical cyclones,
Yeah.
thunderstorms,
Uh-huh.
and tornadoes.
They're all intense in their own way.
What's the difference between all those? They all seem pretty intense.
They are all powerful in their own right, but they form in very different ways
Okay,
and have distinct characteristics.
gotcha.
So let's start with the big ones.
Okay.
Extratropical cyclones and tropical cyclones.
Okay.
Both are swirling storm systems
Uh-huh.
with low pressure at their centers,
Okay.
but they form in very different ways.
Okay.
So are extratropical cyclones the kind of storms we often see in the mid-latitudes?
Mm-hmm.
The ones that bring lots of rain and wind during the fall and spring?
Yeah, like I always think of them as like nor'easters,
Yeah, that's a great example.
the ones that hit the East Coast.
Exactly. Those are classic extratropical cyclones. Okay.
They're big swirling storms that sweep across those mid-latitudes,
Okay.
and they form along the boundary between cold polar air and warm subtropical air.
Gotcha.
That clash of air masses creates a swirling low-pressure system that can span hundreds of miles.
And those are the ones that usually move from west to east. Right.
You got it. Steered by those prevailing westerly winds we talked about earlier.
Gotcha.
Tropical cyclones, however, are a different beast altogether.
Okay.
They don't need a clash of different air masses to form.
So those are the hurricanes and typhoons, the
Exactly.
ones that spin up over warm tropical oceans.
You got it.
Okay, cool.
Unlike extratropical cyclones, which feed off that contrast between warm and cold air masses, tropical cyclones get their energy from the warm, moist air rising over tropical oceans.
Oh, so they're fueled by the ocean's heat.
Exactly. It's like their fuel source.
That's really interesting. So they form in very different ways,
Very different.
but they both involve that swirling low pressure at the center, right? Low pressure is the common denominator.
But aren't tropical cyclones a lot smaller than extratropical cyclones?
They are indeed.
Okay.
It's a bit of a paradox, though.
Okay.
Tropical cyclones might be more compact, but they pack a much bigger punch,
Oh, really?
much higher wind speeds, torrential rainfall,
Wow.
and they can generate something called a storm surge.
A storm surge.
Yeah. Have you ever heard of that?
I've heard of it, but I don't really know what it is.
Okay, so imagine a hurricane, like a giant fan,
Okay.
pushing water towards the shore as it spins. A storm surge is a rise in sea level caused by that powerful wind.
Oh, wow.
And it can cause devastating coastal flooding.
Oh, no.
In fact, storm surges are often more destructive than the hurricane's winds themselves.
Wow, that's terrifying.
They are a serious threat.
So we've got these huge, swirling extratropical cyclones and these smaller but incredibly intense tropical cyclones.
Right, size isn't everything.
It's like a weather war zone out there.
Nature can certainly put on quite a show.
It really can.
And then, of course, we have thunderstorms and tornadoes,
Right.
which are smaller scale events,
Oh, okay.
but they can be incredibly powerful and dangerous in their own right.
Yeah, those are the ones that seem to pop up out of nowhere.
Yeah, especially during the summer.
Yeah. What causes those sudden thunderstorms?
Well, thunderstorms are basically giant towers of cumulonimbus clouds.
Okay.
Formed by warm, moist air rising rapidly in an unstable atmosphere.
Right.
Think of it like a pot of water boiling on the stove.
Okay.
The heat causes bubbles to rise. And in the atmosphere, that rising, warm, moist air creates those thunderheads.
Gotcha.
They can bring heavy rain, lightning, hail, and those strong, gusty winds we often experience.
Okay.
Yeah.
And tornadoes.
Tornadoes.
Those are the ones that are like terrifying spinning funnels of wind.
They are?
They can rip apart houses and everything.
Exactly.
How do those even form?
Tornadoes are a force of nature unlike anything else.
Yeah, they are.
They're actually spinning columns of air that extend downward from powerful thunderstorms.
Wow.
They form under very specific conditions,
Yeah.
usually involving strong updrafts and wind shear.
What is wind shear?
Wind shear is a change in wind speed and direction with height.
Oh,
So it's like the atmosphere gets itself tied in a knot,
wow.
creating these incredibly concentrated vortices of wind.
So I remember reading that tornadoes are the most violent storms on Earth.
They are incredibly powerful.
Yeah.
They can pack wind speeds of over 300 miles per hour.
Wow, that's insane.
Their destructive power is concentrated in a very narrow path,
Right.
which makes them incredibly dangerous.
Yeah,
But thankfully, they're also relatively short-lived and localized.
that's good.
So, we've covered a lot of ground here,
We have.
from those gentle breezes to those monstrous hurricanes.
Yeah.
And it's all driven by these basic principles.
It's amazing.
Pressure differences, heating and cooling,
Yeah.
the Earth's rotation.
It's incredible how it all combines to create this intricate and powerful weather machine.
It really is a marvel of nature.
It is, and we're just starting to understand it.
That's right. The atmosphere still holds many mysteries for us to unravel.
That's true.
Yeah.
Well, on that note,
Okay.
maybe we should take a quick break,
Sounds good.
and we'll come back and delve into some even more specific examples.
Looking forward to it.
Okay, so we're back, and we've been talking all about these big forces that shape our weather.
Right. These global patterns.
Yeah, but you were about to tell me about some more specific examples.
Yeah. Those local winds we were talking
Right,
about,
right.
like sea breezes and mountain winds?
Mm.
Those are driven by the same principles of pressure differences and heating and cooling,
Okay,
just on a smaller scale.
right. So, like, how does that work exactly?
Okay, well, let's start with sea breezes.
Okay.
So during the day,
Huh?
the land heats up much faster than the water.
Right, because the water has a higher heat capacity or something?
Exactly. It takes more energy to raise the temperature of water.
Okay.
So as the land heats up,
Yep.
the air above it warms up too.
Okay.
And warm air rises, remember?
Right, because it's less dense.
Exactly.
Right.
So that rising warm air creates an area of low pressure over the land.
Gotcha.
And since nature kind of hates a
Right.
vacuum,
Right, abhors a vacuum.
exactly, the cooler, denser air over the sea
Yeah.
rushes in to fill that space.
Okay.
And that's what creates that cool sea breeze you feel at the beach.
So it's like the land is breathing out warm air,
I like that analogy.
and the sea is breathing in cool air.
That's a great way to visualize it.
Like a big inhale, exhale.
It is. And then at night, the whole process reverses.
Oh, right, because the land cools down faster than the water?
Exactly. So now the cooler air is over the land,
Mm-hmm.
and it flows out towards the warmer air over the sea.
Okay, so the wind direction actually changes.
Yep, it shifts.
That's so cool. I've definitely noticed that.
Yeah, it's a subtle change, but you can feel it.
Especially like as the sun is setting, the
Exactly.
wind kind of shifts.
Yeah, it's like this invisible dance between the land and the sea.
And it's all driven by these temperature differences.
Exactly.
So is the same thing happening with mountain winds?
It is. It's the same basic principle.
Isn't
During the
it?
day,
Huh.
the sun heats up those mountain slopes.
Okay.
And just like with the land at the beach,
Right.
the air above those slopes warms up and rises,
Gotcha.
creating an area of low pressure,
Okay.
and that draws in cooler air from the valley below.
So it's like a valley breeze.
Exactly. And then at night,
Yeah.
the slopes cool down,
Hmm.
and the denser, cooler air flows down the slopes into the valley.
So it's like a mountain breeze.
Exactly. So
Interesting.
whether it's the land and the sea or the mountains and the valleys,
Yeah.
it's all about that differential heating and cooling, creating these local wind patterns.
It's like the mountains are breathing too.
They are. It's
Hmm.
amazing how these same principles apply at different scales.
It really is. It's like
Yep.
these big forces are playing out in miniature.
Exactly. And, these local winds might seem small
Uh,
compared to those global wind patterns, but they can have a big impact on local weather and ecosystems.
right, like those sea breezes can really cool things down on a hot day.
Exactly. And mountain winds can influence things like wildfire behavior.
Oh, wow, that's interesting.
So even though we're focusing on these big atmospheric processes,
Yeah.
it's important to remember that
What?
these smaller scale phenomena
Yeah,
are also incredibly important.
they are.
Yeah.
Okay, so we've talked about these local winds,
Mm-hmm.
and we've talked about global wind patterns.
Yeah, the big picture stuff.
But what about all those crazy weather events we see?
Like storms.
Yeah, storms,
Mhm.
hurricanes, tornadoes.
And those are the real attention grabber.
They are what causes all that.
Well, storms are basically a way for the atmosphere to release energy.
Oh.
All that heat and moisture we've been talking about
Mm.
has to go somewhere.
Right.
And sometimes it gets released in these dramatic events.
Okay, so how does that work?
Well, there are different types of storms, as you mentioned,
Right.
and they form in different ways.
Yeah.
Okay.
But they all involve some kind of instability in the atmosphere.
Okay, so what does that mean, instability?
Basically, it means that the atmosphere is primed for some kind of dramatic change.
Okay.
It could be a rapid rising of warm, moist air
Mm-hmm.
or a clash between different air masses.
Okay, like those cold fronts and warm fronts we talked about?
Exactly. So let's start with thunderstorms.
Okay, those are the ones I'm most familiar with.
Yeah, those are pretty common in many parts of the world.
Yeah, especially in the summer.
Right. So thunderstorms form when you have warm, moist air near the ground
Uh-huh.
and cooler, drier air aloft.
Okay.
That warm, moist air starts to rise.
Right, because warm air rises.
Exactly. And as it rises, it cools and condenses,
Okay.
forming those towering cumulonimbus clouds we call thunderheads.
Right. Those are the ones that look like big anvils.
Precisely.
Yeah.
Inside those thunderheads,
Yeah.
you have all sorts of crazy stuff going on.
Like what?
Well, you've got strong updrafts and downdrafts.
Mm-hmm.
Lightning. Yeah. I love watching lightning storms.
Yeah, they're pretty spectacular.
Yeah.
Hail.
Hail can be scary, though.
It can be, especially if you're caught in a hailstorm.
Yeah.
And of course, those heavy downpours of rain.
Okay, so it sounds like a lot of energy is being released.
Oh, absolutely. Thunderstorms are like the atmosphere's way of letting off steam.
Wow.
And sometimes those thunderstorms can spawn even more intense phenomena.
Like tornadoes.
Exactly. Tornadoes are these incredibly powerful, rotating columns of air.
Yeah, they're like those spinning funnels of wind you see in the movies.
Exactly. But in real life, they're even scarier.
Right.
They can pack wind speeds of over 300 miles per hour.
Wow.
And they can cause incredible damage.
I've seen the pictures. It's terrifying.
So how do these tornadoes form?
Yeah. I've always wondered about that.
Well, they usually develop from supercell thunderstorms.
Okay. What are those?
Supercell thunderstorms are basically thunderstorms on steroids.
Okay.
They have this rotating updraft called a mesocyclone.
A mesocyclone.
Yeah, it's like a giant spinning top inside the storm cloud.
Wow.
And under the right conditions, that mesocyclone can stretch and tighten,
Right.
forming a funnel cloud that reaches down to the ground.
And that's a tornado.
That's a tornado. Now, thankfully,
Yeah.
tornadoes are relatively small and short-lived
Okay.
compared to other types of storms,
Right.
but they can still be incredibly destructive.
Yeah. Those wind speeds are no joke.
Definitely not.
Okay. So we've talked about thunderstorms and tornadoes.
Mm-hmm.
What about those really big storms?
Like hurricanes.
Yeah, hurricanes.
Okay, well, those are officially known as tropical cyclones.
Okay, tropical cyclone.
And they form over warm tropical oceans.
Right near the equator.
Exactly. So you need those warm ocean waters to fuel these storms.
Okay.
As warm, moist air rises over the ocean,
Mm.
it cools and condenses, forming clouds and releasing heat.
Okay.
That heat further warms the air, causing it to rise even faster.
Gotcha. So it's like a feedback loop.
Exactly. And as more air rises, air from the surrounding area rushes in to replace it.
Okay.
And thanks to the Coriolis effect.
Right, that spinning Earth thing.
Exactly.
Yeah.
That incoming air starts to spin.
Okay.
And if the conditions are just right,
Yeah.
that spinning mass of clouds and thunderstorms can organize itself into a tropical cyclone.
Wow. So it's like all these different forces coming together.
Exactly. It's like a perfect storm of ingredients.
And what about those different categories of hurricanes?
Oh, right. Like category 1, category 5?
Yeah, what does that even mean?
Well, those categories are based on the hurricane's wind speed.
Okay.
The higher the wind speed,
Mhm.
the higher the category.
So category 5 hurricane is the most intense.
Exactly. It has the highest wind speeds.
Wow.
And those high wind speeds can cause incredible damage.
Yeah, I've seen the videos. It's like houses just get ripped apart.
It's devastating.
And what about that storm surge you mentioned earlier?
Oh, yeah. Storm surge is a major hazard with hurricanes.
Okay.
It's basically a rise in sea level caused by the hurricane's powerful winds.
Gotcha.
As the hurricane approaches the coast, those winds push water towards the shore,
Okay.
creating this dome of water
Oh.
that can surge inland.
And that can cause flooding.
Oh, absolutely. Storm surge can cause massive flooding,
Wow.
often more destructive than the hurricane's winds themselves.
That's scary.
It's a serious threat.
Okay, so we've talked about thunderstorms, tornadoes, and hurricanes.
Mm-hmm. Quite a tour of storms.
It is, yeah. What about those extratropical cyclones?
Oh, yeah, those are the big ones.
Yeah, they're the ones that hit the mid-latitudes, right?
Exactly. So remember those fronts we talked about earlier?
Right, the boundaries between different air masses.
Yep. Well, extratropical cyclones form along those fronts.
Oh, okay, interesting.
Specifically, they form along the polar front.
What's the polar front?
The polar front is this boundary between cold polar air and warm subtropical air.
Okay, gotcha.
And as those two air masses interact, they can create these swirling low-pressure systems. And those systems are what we call extratropical cyclones.
So they're kind of like hurricanes, but they form differently.
Exactly. They have some similarities,
Okay,
like the low pressure and the rotating winds,
right.
but they form in a different way.
Gotcha.
And they tend to be much larger and less intense than hurricanes.
Okay. But they can still bring a lot of rain and wind.
Oh, absolutely.
Yeah.
Extratropical cyclones are responsible for a lot of the stormy weather we see in the mid-latitudes,
Right.
especially during the fall and spring.
Yeah. Those are the times when we tend to get those big storms.
Exactly. So, we've covered a lot of ground here.
We have.
From those tiny little sea breezes to those massive extratropical cyclones.
Yeah. It's amazing how it all connects.
It is. And it's all thanks to those basic principles of atmospheric circulation we've been discussing.
This deep dive has definitely given me a whole new appreciation
Yeah.
for the power and complexity of our planet's weather.
It's truly remarkable.
It really is. Wow.
Yeah.
This has been a wild ride
It has.
through the atmosphere. We've gone from these like invisible forces of pressure
Right.
to these like awe-inspiring storms.
Yeah, it's all connected, isn't it?
It's crazy. It's like,
Yeah.
who knew there was so much going on?
Right.
Literally right above our heads all the time.
It's easy to forget about it.
It is. Yeah, you just
Yeah.
kind of take it for granted.
Mhm.
Well, let's do a quick recap,
Okay, sounds good.
just to make sure it all sinks in for everyone.
Right.
We started with atmospheric pressure. that
Right.
invisible force
Mm.
created by the weight of all the air above us.
Yeah, that column of air.
Yeah. And we learned that differences in pressure create wind.
That's the driving force.
And wind doesn't just blow in a straight line
Nope.
because the Earth is rotating,
Right.
which causes that Coriolis effect.
That's right. Deflecting the wind,
Yeah.
creating those swirling patterns.
And we talked about those massive cells of air.
The Hadley-Ferrell and polar cells.
Yeah, acting like giant conveyor belts.
Yeah. Moving that heat energy around.
From the equator to the poles.
Trying to even things out.
Yeah. And of course, we can't forget the oceans.
Oh, the oceans are a huge part of this.
They play such a big role in the weather.
Absolutely.
You know, the winds drive those ocean currents. And the oceans, in turn, influence those wind patterns.
Right. It's a constant back and forth.
It's amazing.
It is.
Then we zoomed in on those local winds.
The sea breezes, the mountain winds.
It's all driven by those same principles.
Exactly. Pressure differences,
Yeah.
heating and cooling.
We talked about air masses, too,
Those big bubbles of air.
with different temperatures and humidity levels.
Yeah, each with its own personality.
Yeah. And how their collisions create those fronts
Right.
and lead to those dramatic weather changes we see.
The cold fronts, the warm fronts, it's
Yeah.
all a big dance.
It is.
Yeah.
And of course, we couldn't leave out those awe-inspiring storms.
Yeah, the storms are the main event.
They are. We talked about those sprawling extratropical cyclones
Yeah.
that hit the mid-latitudes,
Mm-hmm.
those compact
Mm-hmm.
but incredibly intense tropical cyclones.
Right. Those localized but powerful thunderstorms and tornadoes.
It's amazing how much energy the atmosphere can pack.
It really is.
Yeah.
This deep dive has really given me a whole new appreciation
Yeah.
for how complex and interconnected
Absolutely.
our planet's weather systems are.
Yeah, you start to see the patterns.
Yeah, you do. And it's not just something that happens out there.
Right.
It's all driven by these like invisible forces and global patterns.
It makes you realize we're all part of something much bigger.
Yeah, it does.
Yeah.
Well, I think that's about all the time we have for today.
Right.
But this has been an incredible journey.
It has.
We've learned so much about the forces that shape our weather.
And there's still so much more to learn.
There is, yeah. So much more to explore.
Mm-hmm.
So for all you listeners out there,
Mm-hmm.
next time you check the weather forecast, or feel the wind on your face,
Yeah.
or watch a thunderstorm roll in,
Uh-huh.
take a moment to think about all those fascinating forces at play.
Those invisible pressure gradients that's spinning Earth, those giant air masses colliding, that incredible exchange of energy between the atmosphere and the oceans.
It's all happening all around us.
It really is. And it's all part of this amazing dance
Yeah,
that creates the weather we experience every day.
it's a beautiful thing.
It really is.
Yeah.
Well, that's it for this deep dive into atmospheric circulation and weather systems.
Thanks for having me.
Thanks for joining us, and we'll see you next time on The Deep Dive.
Bye, everyone.